So we have this simple program. The feasible area is here, and I want to solve it using Julia. Let me go. What you can do when you have to solve something with Julia, you take the slides I gave you, or I can give you, and you look, for instance, of the first Julia program. And what you can do, you take this, let's say this framework, this code. Don't do copy paste. I think it's not a good idea copy pasting things, because you learn nothing by copy paste. So I won't do copy paste. Even this stupid effort of just writing things, it may pay off. Now I will start writing the code, and I will solve the exercises with you using J. This way you remember things. I can use
dependency, something like.
Yeah, I have installed everything as for me, but if you have CB,
I already installed it.
You have everything installed. That's nice. We can use CBC or GLPK for instance. We always have a model, so because by writing the code we understand a bit what happens. I have a model M, and I will give it the optimizer. The optimizer will be the GLPK one. And this seems quite easy. We always use this character at variable M is the model, X greater than 0, because I repeat, we want to solve this on non-negative variables. Okay, you follow? So variable, you know, on the slides here, we had something int. Do you know what it means? Integer. But in our case, for the problems we want to solve here, is not integer. So we can only write this. Okay? This is why it's not really copy paste. We need to pay attention. Same for y. And then, look how the objective is written, not very difficult. Objective M max. Our objective is 5x plus 4y. Then I think we have constraint M. What do I have? X plus y less than equal to 5. And constraint 10x plus 6y less than 45. We have this. Okay. It's not very, very difficult.
So what I want to understand.
Yes.
In the graph, what is the non-negative value?
The non-negative part is written, if you want, here.
Yes.
Because we say x and y are non-negative. If I understand the question.
Okay.
You see the value of x are here.
Yeah.
So only non-negative.
Okay.
This is the question, or it was about something else?
Okay. This is value of
It is not negative. The whole space of x and y is this part of the space. Okay. Only positive x and positive y. Okay. Don't hesitate for questions. I am all yours. So we have this. Then I have the model to optimize it. Optimize, so I can do it like this. Optimize exclamation M. Okay. And then I can use the print the objective value, println objective value of M. And if you want, println something like, I will change x and y, and I will write it value dot x, value dot y. So if everything is fine, let me look over this. If everything is fine in this program, you see, if everything is as expected, this program, this short Julia program, this is everything I have, will solve this, okay?
Yes.
The feasible area is here, and the optimal value should be this point here, which means x is about 3.8 and y is about 1.2. Finger crossed. You know what finger crossed, because when you first execute the first program, don't worry. First it may take time, and Julia takes time,
Yes.
but you may always have some error. It's
Yeah.
not the end of the world if you have an error. Okay, but I will try to execute it using my software that I have here. It takes some time. Live GLs is the name of the file. Okay.
And the software you
It's something only of my. We have a problem at line 6. This is what you should do as well. So this is important for you to follow me as I try to solve the errors, because everybody will have errors. If I have an error here, it's in LiveGL. This is the name of the file. At line 6. Something is not right at line 6. Did you see what happened?
Yes.
I have 2x.
Two variables.
X.
The same.
Yes, this may happen. This is another reason not to do copy-paste. If I did a copy-paste, the code would have been perfect, but we learn nothing because it's
Just
perfect.
copy.
But now if you type it yourself, you see a bit how you can make an error, how you can correct it. Just saying copy-paste is cool, it works, is not enough. This is for the second part of the course. This is the computer class of today. What happened is not written perfectly here, but x and y, I have x actually is 3.75. I need to add a space, and y is 125. Don't worry about this error. This is numerical errors. I will write it this way. X is this, you follow me, and y, it's only the way I print it, okay?
Okay.
And I will execute it again. This is x, 375, and y is 125. This seems correct now. This is the optimal solution in real numbers here. No? Look, if you want, what we can also do. Let me write a comment here. So x is 375, he said, and y is 175. That's it. Is the first constraint satisfied? The first constraint is x plus y less than 5. And if I replace 75, okay? If I replace the values, I have this plus, sorry, I wrote, it was 25. Okay? sorry. This is perfectly satisfied. And since we have equality, this means that this xi point has to be somewhere along this line. You follow me? Okay. Really don't hesitate to stop me. On the second constraint, I have 10x plus 6y less than 45. Let me replace x 325, 6, 175. What is this? This is this. And here I have a bit more complicated. Yes, 10 or something. I will I have a small calculator, and I have 6, 10.5. It's a bit strange, it's not 45.
No, it's less than.
It's less than.
Yeah.
It's less than. Did I correctly write 45? It's less than.
Yeah, that's 44.
So this gives 43. Let me check if something is wrong or not. No, or not, because I wasn't expecting this at all. Sure. Right? Sorry, these are the good values of x and y. So now when I write 10 times x plus 6 times y less than equal 45, I have 10 times 375 plus 6 125. That's it. I don't know, 27.5 plus this 7.5. And this now I have equality. Okay. Okay. So this is how you can write a Julia program to solve a simple problem. Okay. I think you need to pay it. Yes.
Can you repeat please how you execute the program once you...
Julia?
Yeah.
Actually, what you should generally do, I do it using a very particular software, but what you should generally do, look what happens here. I have here a file called live.gl because it's the program that I write live. What happens is that you need to take a look where is your folder, and my folder on Linux is on / data tac. So what you have to do, you start a terminal, okay, and you go to that folder. And in this folder I type ls, and I see live.gl here. And now what you have to type is, there are two ways of using Julia. Either you type Julia live.gl like this, but the same in Windows. In both Windows and Linux, you have two ways of using Julia. You write Julia and the name of the file, but this way of doing it will take some time. Please pay attention. It takes around 7 seconds. I can even count the number of seconds. It's quite a huge time if you do it. However, see, let me check how many seconds it takes by putting the time command before. I can wait. Time will give us the time as well. I don't know, it takes 13 seconds. This is huge for me. But what you can do is you type Julia with no argument.
Yeah.
It will start the interpreter of Julia. And now you write include and you give as argument live.gl, sorry. So now you write this in the Julia interpreter. The very first time it will take some time, same as before.
It's taking more time.
A lot of time. But if you execute it the second time,
It will be fast.
yes, if you execute it the second time, it will do it right away. You don't have to wait. This means I can even start to change things here. I don't know, we add a new constraint, whatever, and I can execute it. It's the same solution, but it's executed right away. Pay attention when you write things here. Sometimes the spaces are important in Julia.
Yes, that's the next question that because when I give space, the result is different.
Yes, if I have just put a space after m, after a variable, and it does not like it. I have an error. You see, just a space here, and you have an error. I cut the space. There is no error.
Yeah.
Same for objective, I think. Problem. Same for constraint. Okay. And also pay attention to what is, you know what I don't like about Julia sometimes? Julia relies on an external optimizer. Let me give him something crazy, something that is not right. I ask x plus y to be less than 5, and then I'll ask x plus 5 to be greater than 10. This is clearly not possible. Because I ask something to be less than 5, and the same something to be greater than 10. Okay, it's not possible. It will work. Let me see if this is what happened. The problem is if I change the solver, I will have something correct. Actually, the problem is GLPK optimizer is not actually part of Julia. GLPK optimizer is an external solver that does give you a solution whatever happens. Whatever you ask him, he will give you a solution. Only if you query that solution afterwards, it will give you that solution is not feasible. If I move to CBC, it will be different, CBC. Thank you. Now it will be different. Now, did you notice? They do tell me that the problem is infeasible. So basically, it's not the same, exactly the same, using one solver or another. Okay? For such if you ever have this kind of problems, the best things to do is to look over the internet, you type Julia ask solution status, something like this. Julia jump, maybe. Let me see if I well, let me try this termination status, for instance. I go back to this code and let me write here termination status M, something like this. You see, this is the code that does give me this solution, okay? But when I ask him, let me call him, I won't say he or she because it's a software, but I should say it, but I will say him. If I ask him to give the termination status of the solver, the termination status is infeasible. Basically, he tells me that the solution that he has just printed is infeasible. Why? Because I asked here for something crazy. But if I remove the second constraint, which made the model infeasible, and I execute again Julia, it's the same as before, only now the solution is optimal. So, but if you pay no attention and you don't say that the solution is optimal, if you don't ask him to say if the solution is good or not, he will actually give you a solution, whatever you ask him. Only that, by the way, is not feasible. It's like if you are asking something to give you something, whatever you ask, he will give you, but you need to ask him if that works or not. That's it.
And what about space between the parameters?
Here, I think the spaces are fine. Yes, here you can have spaces. Let me check, but oh no, problems with spaces. Objective value, no, you need to put. Sometimes spaces are okay here. Many problems with spaces. You should never put any space. If you try to avoid spaces, let me try. Oh, sorry, avoid spaces. I think maybe here you have the right to do it when you separate the arguments. Okay. This is how we work with Julia. Okay. Let me now move to question 3 that you asked. What I ask here, is the optimal solution in real numbers very close to the optimal solution in integer numbers? Do you understand this question? I want to know if the optimal solution in real numbers, what is the optimal solution in real numbers? Is the solution that I have just printed. This is the optimal solution in real numbers. You know what I mean? Okay, this is the point. This is the optimal solution. Is this solution close to the optimal solution in integer numbers? What do I mean by that? I will now change the model a bit, and I will give here for the variable integer int. See, I put int here. Now I change the problem. If I do this, I change the problem. It is no longer a problem in real numbers, but in integer numbers. What will happen? This point can no longer be optimal. You follow me? So what can he do in such a case? Let me focus on the feasible area. So this is the optimal solution in real numbers. Pay attention. Can it return this point? No. This does not satisfy both constraints, because the feasible area is at the left of these two lines. But it can give me as a solution either this or this, the integer values, you see? Or it can give me this or this. In your, what do you think it will give me? In integer number, the solution. This or this? The lower point or an upper point? The upper point I think is better, because we maximize this. We have the interest to have both x and y as big as possible. But I don't know, maybe this is even better, you know. I think which one is better, this one or this one? We can simply compute the objective values in these 2 points. Here I have x3 and y2. So, sorry, let me write a comment. You computed 33 for this one. So, I will say x and y. If x and y are 3 and 2, I have objective equals 5 times 3 plus 4 for 2, which is 33. Yes, thank you. If I have x and y, here I have 1, 4. 1, 4. This will give me an objective 5 times 1, 4 times 4, 21. So this one is better. I think this will be the optimal solution in integer number, but I will ask Julia about it. I will ask Julia to compute it. Okay, so to ask Julia to compute it, what does it mean? I have just added the keyword integer here. It's not the keyword integer, but int.
Is it type?
It's a kind of type. It's a kind. Yes, and we have 3 and 2. Okay. Okay. Do you understand the second question here? Can you say the integer solution that is closest to the non-integer solution is the best one? You understand the question? You take the real solution in real numbers. You take the closest integer point, and you ask if that is the optimal solution in an integer number. And the answer is not exactly. We would like to be like that because this would simplify our life. But if you pay attention, it's not exactly the case. Because why? Let me zoom. I have just zoomed here. This is the optimal in real numbers. Strictly speaking, the closest feasible integer point is this one, while the optimal solution is here. Strictly speaking, this is the closest integer point. See? So, It can be a bit tricky. This is one way we could try, but generally speaking, if you take the solution in real numbers and you take the closest point, integer point, usually it's more or less okay, but not optimal. Okay? Let me change the model a bit. Do you know what happens if I put, instead of integer, just for your knowledge, for your information, if you put bin, do you know what happens?
No.
This means binary. Binary variables, this can be 0 or 1. Okay?
So it should be 0.
It makes not much sense to solve this in binary variables, because if we do it, this means x can be 0 or 1 and y can be 0 or 1. In this case, I think it will give the solution 1, 1. Let's test it to be sure, but yes. But it does not make much sense in this case to use binary variables. In the computer class of last week and in the computer class you will have today, we may have to solve also a knapsack problem, where for each article I ask a question: do I take it or not? In this case, I will have a binary variable, because for each article, yes, for some problems, the nature of the problem makes it interesting to be solved using binary variables, you see. But here is not the case. Any question here?
So for exercise 3, we just want put the int.
Yes, in terms of in the Julia code, yes, we just put int, and it will solve it. But pay attention, it's difficult to find. It's difficult to say where is the integer solution with regard to the solution in real numbers. Sometimes they are very, very close. Sometimes they are not so close. But if you ask Julia to do it, Julia should not lie. It will give you the answer. It's interesting to solve this. What do you think about exercise 5? 4 is not interesting, 5 is interesting. Can you change one of the constraints by modifying the right hand side? Right hand side is here 5 or 45. This is the run. This is the right hand side, okay? By one unit, so that the optimal solution in real numbers becomes integer. Basically, I want to change the right hand side so that the optimal solution in real numbers becomes integer. Please pay attention here. I want to do here, sorry. I just want to find this as optimal. Yes?
I think if you change the constraint, like you put like instead of 5 you put 6 or something.
Yes.
So maybe the integer solution is still the same.
Yes. Because what I want to do, I want to have the real solution. I want to make the real solution integer. Look, this is x plus y equals 5. Pay attention, this point here already satisfies this constraint, but it does not satisfy the second. But let me just go a bit above by one. Instead of 45, let me put 46. This is because if I do this, what happens? This constraint 2, this, the second constraint, will move a bit right, to the right. And if I zoom here, if I zoom enough here, what will happen when these constraints move a bit right? It will actually go through this point. So let me go to the Julia code and let me say 46. But the magic here, this is the magic I want to tell you about. I don't need to say integer. Now I solve the problem in real numbers. But when I solve the problem in real numbers, look, modulo the numerical errors, if you ignore the numerical errors, the optimal solution in real numbers is x is 4 and y is basically 1. But all optimization software you will always use to solve this kind of problems will have some numerical errors. When you see such a thing, this means 1. Any question?
I didn't. Why we don't need to change the first constraint?
What do I need to change?
No. Why we don't need to change? We just change the second for 6.
Why I leave the first constraint like this?
Yes.
Because my goal was to find, my goal was to find solution x equals 4, y equals 1. Okay? And this already satisfies x plus y less than 5. We don't need to touch this because I have this means 4 plus 1 less than 5. This is already satisfied. The first constraint is satisfied by this point. This is the point I'm speaking. This is the point I'm speaking about. x4, y1. Okay. And what's the advantage of such a program? The solution in real numbers is integer. So in this case, we don't need it's easy to solve the problem in integer numbers. Okay, in computational terms, solving a linear program in real numbers is considered a very, very easy problem. What is difficult is when you switch to integer numbers. But for this particular case, if the optimal solution in a real number is integer, the problem is easy, even in integer numbers. You see the reasoning? Okay, any question? What do you think it's interesting to solve other questions from the last computer class, or we can see this later? We should do 6 or 7. It's only up to you because you are not so many. Okay, now you are at least 8, which is better, but
we can solve 6 and 7.
6 and 7? What?
Provide the solution?
This is the solution what I provide now, and I will put this video online, and you will be able to see this on YouTube if you want. So for 6, is the question more or less clearly written? What happens if you allow x and y to be negative and I change the objective function into 4x and 5y? Can the objective become not finite? Solve the question first in your mind and then check this with Julia. So what happens? I change the objective function into this one. Let me first do this with Julia to see how this changes the story. Okay, I change the objective function into 4x plus 5y. 4x, 5y, and I return to 45 here as initially. Okay, now something strange will happen. I will execute here. The optimal solution will move from here. It will move to a very different point, because the objective initially was where is the optimal point here now? Is x0, y5. It's here. It moves from here to here. Why? Because I changed the objective function. Previously, the objective function was maximizing towards this direction. And what does it mean? So what did I have before? I will even write. What is the difference between maximizing? I had 5x plus 4y and 4x plus 5y. What's the difference? Look what happens on along the first constraint. What happens along the first constraint? I will write the point along the first constraint on the first constraint satisfy x plus y equal 5. So, among all solutions, all x and y that satisfy x plus y equal 5, these points are situated on this line. Which is the best one if you maximize 5x plus 4y? If you maximize 5x plus 5y, basically you say something like x is more expensive than y. X brings more profit than y. Imagine this was your profit from doing two actions, x and y. If you gain 5x plus 4y, you have the interest to do more x than y. But if you have 4x plus 5y, if this is what you will gain, if this is the money you will get, you will have interest to have less x and more y. Imagining, you understand me?
So that's why the optimal solution is in the y-axis?
Yes. In the second case, it has the interest of maximizing y up to here and minimizing x. Okay? For the initial function, he has the interest to make as much x as possible, and it will go here. It cannot go any further in the initial case because I have a second constraint. But I hope is this clear for you. Imagine you have 5 hours to work something, and you need to spend this time between two tasks, x and y. If x gives you more money than y, you'll take the maximum amount possible of x. If y brings you more money than x, you'll prefer to do as much y as possible. So this is what happens as long as I stay on non-negative variables. The solution is here. Now, the question here was, what happens if you allow the variables x and y to be non-constrained, to be positive or negative? Because remember, the whole story here was going with x and y positive.
Yes.
What happens? What do you think it will happen if you allow now x and y to be
Negative.
yes, positive or negative?
The optimal area or something.
It will go to maximize y. It will go along this constraint. What did it happen just right away? It moved like this to maximize y until x becomes 0, because it will not allow x to be below 0. But if I allow x to go below 0, it will actually go like this up to infinity, basically. Because okay. And how can you change this in Julia? Look, here, when I declare the variables, I said they are positive, not negative. Now let me do it like this. It gives you a solution, but if you pay attention, it will tell you dual infeasible, boom, whatever. It's not the same as before. Because before the solution was optimal, now it's dual infeasible. I don't know if you remember, I think you don't remember from linear programming, from the linear programming course. But if a solution is dual infeasible, this means it is the solution is unbounded on the original program. This is a bit of theory, but basically, even if you don't remember this theory, trust me, saying that is dual infeasible means that the objective is unbounded. Okay? It may be interesting to change the solver instead of GLPK CBC, just to see how it will make it. It's a bit different, but it gives this is like an error, dual infeasible, but the output is different, but it's the same idea, dual infeasible, which basically means that the original model is unbounded. Okay. Any question related to everything I have just discussed? You can give me some exercises if you want. You can. Do you have any problem of this kind in real life? I mean, in some sense, every decision you take in this life, it's a kind of optimization question. What should I do now to, I don't know, to reduce the cost? What can I do now to maximize the profit? Every time you go into a shop to buy something, you have a kind of optimization problem. What should I buy today, given that, I don't know, I'd like maybe to save some money, but I need to eat well, I don't know, I need to invite some friends, so of course we don't formalize problems this way, but we could do it. Should we move to point 7, or do you think it's interesting?
Yeah.
But okay, we change the problem as follows. We allow each of the constraints to be slightly violated, like if you had a kind of elastic knapsack. I mean, when you go into a shop, one of the constraints you have is I have 10 euros in my pocket, I can buy whatever I buy, but I cannot go beyond the 10 euros, okay? I think you are younger than me. Now you all have credit cards and stuff, but some years ago, some 20 or 30 years ago, there were no credit cards. The money you had in your pocket was a really hard constraint into a shop, because if you had $20 in your pocket, there was no way you could exceed that. But with the modern banking system, you can always buy on credit. You always have a credit card, and you can always play a bit with the limits. Okay, you understand what I mean? This is the idea here. Even every budget constraints we may have, today they are a bit flexible. A bit flexible. So this is the idea here, because this is a phenomenon we see in real life. All constraints we may have is not, generally speaking, whatever the nature of the constraints, is not, generally speaking, really less than equal than 45. This 45 can easily become 46, 47. You understand me? It's a parameter. So what can happen here? You may exceed the right-hand side value, the limit of 45, for instance, by some amount C. Okay, this is still less than 2. I don't want to have an excess too large. And this comes at a cost. By exceeding the limit by an amount of C, the profit is decreased by 0.1 multiplied by C. How can we model this new problem? Understand me? I can go beyond the budget by some amount C, but I need to pay in the objective. What's the new problem now? Yes, we add some C here. Yes, but in the objective, it's a penalty in the objective, because it's something we pay. So I will try to write. Yes. So you follow me. I will just write the new problem like this. This is a comment. Okay. This instead of 10x plus 5y less than 45, I will have 45 plus C. The budget, it's a bit flexible. I keep the first constraint as it was. But here I will have max 5x plus 4y minus, this is a penalty in the objective. The profit is reduced by 0.1 C. What do you think? What kind of variable is this C? Integer or real? I think we can allow it to be real. You basically say you can go a bit beyond the budget. Like the budget of any modern state, if you want. Any modern states I know of, they start with a budget when they do it in the beginning, and by the end of the year, they go a bit beyond. This is life, because we can go on credit, something like this. So, how should we add the new variable? I have x. Let me return to positive values to make things simple. And similarly, I add a new variable C. Still positive, okay? And all I want to do here, minus 0.1 C. I can even write it this way or this way. And here 45 plus C. That's it. Okay, on here, this is x, this is y, and I say, and c is, I think you know what I should write, value dot c. Okay, that's it. Exercise 7 was not much more complicated than this one. Okay, let's execute it. It's faster if I do it here. I think yes, let me go back to the original objective function, sorry, because I had just changed the objective function in the previous exercise. Something unexpected happened. I had c equal 5, but what I said in the exercise is c is okay. So what we should have written here, either you can write it like this, or more naturally the other way around, basically. Okay, I think it should work. Okay, c is between 0 and 2. Okay, so now he used all the flexibility he could have had, and thus he increased x and reduced y, and the objective value is 2405. Previously, if I fixed c to 0, I go back to the original question. The objective is 23, okay, 0.75, and now, okay, so by allowing some of the parameters to change a bit, which often happens in real life, all the parameters we have can change a bit, the objective function was improved. Okay.